we're going to talk about discrete probability.
Here's elementary statistics practice test number 2, module 2, covering chapters 4 and 5. Here's chapter 5, discrete probability distributions. Does the table describe probability distribution? What is the random variable? What are its possible values? And are its values numerical? Take a look at the table. We have the x and p of x. When it comes to discrete random variable, we have two columns, one representing the random variable x and one representing its probability x and p of x. The variable x, which is the number of girls in 3 pairs, 0, 1, 2, 3, is a numerical random variable, and its values describe probabilities, summation of a p of x. That means, as always, remember the sum of probabilities, they must add up to 1. So if you look at the second column, we add up those numbers, 0.125. 0.375, 0.375, 0.125. They must add up to 1. The only time they do not is due to round-up error, in which case this number is extremely close to 1. That means it may be 1 point, bunch of zeros and then 1, or maybe 0.9999, many nines, but nevertheless extremely close, which happens due to round-up error. I can't emphasize this enough. You need to know that. And of course, each value must be between 0 and 1.
In a game, you pay 60 cents to select a 4-digit number. If you win by selecting the correct 4-digit number, you collect $3,000. How many different selections are possible?
Excellent. So we have the first thing to worry about, we have 4 digits. That means 4 spots. And as you know, when we say digit, it goes from 0 to 9, giving us 10 for each spot. And it results in 10 to the power of 4 or 10,000. Those are the 4 spots in essence. So you multiply the numbers. The numbers are 10 times 10 times 10, or simply 10 to the power of 4. So 10,000 possible outcomes. What is the probability of winning? By definition is n of winning over n of s. There's only 1 out of 10,000. If you win, what is your net profit? Well, we've already paid 60 cents. So it comes out of that. $3,000 minus 0.6. $2,999.40 would be the net profit. We want to write the probability distribution of net profit. And as I mentioned, it basically has 2 columns, x and p of x. So we are going to write numbers that are going to win. There is only one number that can win, $3,000. The rest are basically those who don't win, losers. The total is 10,000. The probability for each one we are going to write is as follows. First of all, this person gains this much as a net profit. The rest, negative 0.6, because that's how much they paid. Probability of winning is 1 out of 10,000. Then the rest of it, that means 1 minus that is for the rest. So winner, net gain, 1 out of 10,000 x, p of x, and everybody else, negative 0.6. The sign is extremely important. So this is the probability distribution of net profit. The next one asking for the expected value. It's mu or E of X. Mu or E of X. And by definition is summation of X, P of X. So the formula, they call it either mu or E of X. So summation of X and P of X. So that means we are going to multiply these two. So let's multiply these two, let's multiply these two, and then we add them up. That's the concept as far as mu is concerned. So calculate X, P of X. This one times this one, you put it here. This one times this one, you put it here. Now, why am I giving you this? Because also we need that for the interpretation, and the other part, calculating the variance and therefore standard deviation, which uses the formula of summation of X squared P of X minus mu squared, or the summation of X minus mu quantity squared times P of X. Either way is fine. So X squared, that means you are going to square this value and then multiply it by this value. That becomes this first entry. The second one, you are going to square this one, which becomes positive, times this one, you put it here in the following manner. When we do that, we add up these two, becomes summation of X, P of X, and that is your mu or expected value. You add up these two, and it only becomes this part of sigma squared. Add up these two, and here's what we do. We write down mu or summation of X, P of X is negative 0.3. So to do the interpretation, let's also calculate the sigma or standard deviation. That's why we use this last column. Using the formula, all we have to do, subtract the value of mu squared. So we are going to subtract, put this in this value squared becomes positive, subtract it from there, and take a root, because what you have is the variance. Now with the square root, it becomes a standard deviation. There you have it. So therefore, what it means is that on the average, everybody loses this much. Everybody loses about 30 cents. Every player, on the average, including the winner, with the standard deviation of 94.850. Needless to say, because we deal with money, normally we go with 2 decimals, and we would write this as 94.85. So on average, a player or players loses $0.3 or 30 cents per ticket with the standard deviation of 94.85.
A pharmaceutical company receives large shipments of aspirin tablets. The acceptance sampling plan is to randomly select and test 24 tablets. The entire shipment is accepted if at most 2 tablets do not meet the required specifications. If a particular shipment of thousands of aspirin tablets actually has 5% rate of defects, what is the probability that this whole shipment will be accepted?
So when we read this question, we should recognize what's given symbolically. And we realize this is dealing with the case that either it's defective or not, whatever that you're dealing with. In this case is the aspirin. And so there are 2 outcomes, and you're dealing with, therefore, binomial distributions. And anytime you're dealing with binomial distributions, you have to mention 2 things. What is n? In this case is number 24. And what is p? P is known as the probability of success. Now, it may not necessarily represent something positive, but that's the terminology that is used in statistics. So each one has a chance of being defective at 5% or 0.05. So you're dealing with BD, short for binomial distribution. N is 24, and P, the probability of success, it's called. Again, not a good thing, doesn't have to be positive. It's 0.05. And the formula that you see up here, given obviously in the formula sheet, P of X equals N factorial over X factorial times N minus X factorial, P to the power of X, Q to the power of N minus X. This is the formula that we use to calculate the probability distribution of binomial distribution one by one. Mu for the expected value is equal to NP, and sigma equals square root of NPQ. So what is binomial distribution?
Binomial experiment and PD properties. 1, n identical fixed number of trials, each repetition of the experiment. 2, each has only 2 categories of outcomes. 3, probability stays constant. 4, independent trials.
So those are the properties which make up binomial distributions. And what really stands out, 2 outcomes, heads and tails, yes and no, defective, not defective, things of that nature. And the independency is, of course, a huge part. All right, so having said that, the entire shipment is accepted if at most 2 tablets do not meet the requirement. That means we are interested in the probability of X less than or equal to 2. That's really the idea. So let us write a couple of things. Using this formula, plug in the N value and the P value. And to do that, in general, we also have a Q, which is 1 minus P. So P is 0.05. Q is 1 minus that, 0.95. So as long as P is known, Q can be calculated. So they don't have to give us Q. So we want the probability of X less than or equal to 2, and we are going to make this up by putting the N, putting the P, and the Q. Now we are ready to move on. Probability of X less than or equal to 2, because we are looking at most. That's the meaning of at most. It means probability of X equals 0, probability of X equals 1, probability of X equals 2, and we need to add those 3 up. Now, what we have to do if we are doing it manually, in this formula, plug in 0, calculate it. Plug in 1, calculate it. Plug in 2, add them up. Here's your answer. So can it be done by hand? Absolutely. But as always, you can use technology. The commands are second variables, binomial PDF. You can put NPX, and if you enter NP only, gives you all probabilities from 0 to n if using binomial CDF. So I'm showing you how the technology works, and in this case, we want to use CDF. For one individual ones, you use binomial PDF. More than that, you use CDF, which starts from 0 to n. It's important for you to know it does from 0 to n. So for example, if you're interested in something larger, then you have to subtract it from 1. So with that being the case, we put n is 24, p is 0.05, and the x value is 2, then it'll do the job for us, and it give us the answer, and we decide how many decimals we need. To quickly show you that, now over here is the second key, the blue one. So second variables. So you scroll it down with the arrow. You see the first one is binomial PDF. The second one is binomial CDF. You enter 24, the n value, enter. The p-value is 0.05, enter. The x value is 2, enter. Enter again, and it gives you the number that we have down here. All right, that was technology. We are going to look at the next example.
It is known that 70% of managers of all companies suffer from job-related stress. What is the probability that in a sample of 20 managers, exactly 8 suffer from job-related stress?
Clearly, this is a binomial distribution. The reason being, because we are given two things. We are given n and p 70% because either they suffer from stress or they don't. So there are only two outcomes, and they are independent. Therefore, BD or binomial distribution, n is 20 and p is 0.7, which means obviously we are going to use this binomial distribution formula with p being 0.7. Q is calculated as 1 minus that, which is 0.3. Again, Q can be calculated as long as you have P. N and P are called parameters of binomial distributions. So we can plug in into this formula the value of N, which is 20, and the value of P, which is 0.7, and the value of Q, which is 0.3, or you can even write 1 minus 0.7. Either way is fine. And we want the probability of 8. Now, I'm going to plug it in to show you how that works. 20 factorial over this becomes 8, this becomes 12. In any order you put it, it doesn't matter. 0.7 to the power of 8 and 0.3, this is 0.3, everybody, to the power of 12. And you can do the math. Or if you go with the binomial PDF, as it was mentioned, the technology does it for you. I highly recommend you show your work up to here, and then you can use a calculator and come up with the answer. 0.00 and however many decimals, 38593. At most, 8 suffer from job-related stress. X is less than or equal to 8, which means if we were to use this formula, we have to plug in 0, 1, 2, all the way to 8. Needless to say, that is very tedious. But if you write this and the meaning of it, which is simply this, probability of X less than or equal 8 means this, you can use technology. And as you will recall, we use binomial CDF in this case. 20, P is 0.7, X value is 8. And here's the number, and you write the answer with however many decimals you want. In this case, 0.005138. Generally speaking, you really want to take a lot of decimals to be on the safe side, unless they specify how many. All right, we are looking at the same question. We just continue with the next part. At least 9 suffer from job-related stress. Same binomial distribution, n equals 20, p equals 0.7. So at least 9, that means probability of x larger than or equal to 9. Meaning you have to calculate the probability of x equals 9, x equals 10, all the way to n. That's the meaning of it. However, we already know the probability of x less than or equal to 8. And if we use complementary event, all we have to do is subtract that from 1. This, I want you to pay attention to this one, is the same as this one, 1 minus the probability of x less than or equal to 8. We've already done that in the previous part. So we are going to subtract this from 1. So this is the faster way. In other words, if you have to calculate the at least or at most, look at the possibility of using its complement because it may be faster. In this case, it's a lot faster. You don't have to do much calculation. Use the previous one, subtract it from 1. We want to find the expected value. As you recall, mu equals NP. Therefore, you multiply the two values. 20 times 0.7 gives us 14. We want to calculate the standard deviation. Remember, sigma squared is NPQ because sigma was square root of NPQ. Therefore, let's calculate the sigma squared, which means we have to really multiply this one by Q. And now we got to take a root of that because sigma is the square root of that. And we get 2.05. Now, would it be unusual to claim that 7 managers from this sample suffer from job-related stress? We have to look at the usual versus unusual, which was mu plus minus 2 sigma, as you may recall previously. And so we have both values. We have mu, 14, plus 2 times this number, 14, minus 2 times this number. So we go from 9.9 to 18.1. This is the usual range according to this range rule of thumb, as you remember. Is 7 in between? If the answer is yes, is usual. If no, it's unusual. As you can see, 7 doesn't belong there. This is a set theory. In the set theory, looks like an epsilon which is crossed. If there is no cross, it means it's an element of. This means it's not an element of. You don't want to worry about that too much. But 7 doesn't belong here. Therefore, it's considered unusual. Find the probability of a couple having at least one girl among 3 children. Now, probability of at least, the first method, use it as 1 minus probability of none. And we know the probability of both genders are considered to be 50%. So probability of G, probability of B is considered to be 50%. And therefore, 1 minus the probability of none, that means all of them are boys, which is 1/2 to the third. The probability that all are boys. Since there are 3 of them, there are 3 spots to fill up. 1/2, 1/2, 1/2, and 1 minus that, that means 1 minus 1/2 to the third, which is 1 minus 1/8, giving us 7/8. Here's the second method. We can use a binomial distribution with n being 3, p being 0.5, and we want x to be larger than or equal to 1. If p is 0.5, so is q, because 1 minus that is also 1/2 or 0.5. X is 1, 2, 3. And with this at least, probability of x larger than or equal to 1, we want probability of 1 plus probability of 2 plus probability of 3. Again, it's easier to say 1 minus probability of 0. And here's the binomial distribution. We are going to replace the n with number 3, p with 0.5, also q with 0.5. Needless to say, this actually becomes 0.5 to the third. And so when we go through the process and replace the x now with 0, I hope you realize that 0 factor is 1. This is 1. 0.5 to the power of 0 is also 1. Ultimately becomes 0.5 cubed, which is 1/8. And 1 minus that is 0.875 or 7/8, the same as previous one. So you have 2 choices in this case, 2 ways to tackle the problem. If an alarm clock has a 0.9 probability of working on any given morning, what is the probability that it will not work? Clearly, we are looking at complementary events. So probability of winning is given as 0.9. Therefore, probability of not winning, it's W with the bar at top of it. That's a notation. You may have seen a different notation depending on the text, but this is one notation. Sometimes they may use prime. 1 minus that, and that makes it 0.1 or 10%. Now, what if we have two of those? And the idea of two goes back to what's known in statistics as quality control, just to be on the safe side. In that case, probability of each one working is given as 0.9 and not working is given as 0.1. It makes no difference how many you have. Supposedly they are the same. And so probability of not working for the first one. Now, for both of them not working, the notation would be probability of W1 not working intersection W2 not working. And because they're considered independent, you can multiply them individually. That means probability of W1 not working times probability of W2 not working, which means multiply 0.1 by 0.1 and get 0.01. So there is a 1% chance or probability that two such alarm clocks will not work. None of them will work. And that's really amazing. Think about that. We have a 10% chance of failure, which is horrible, by the way. But by making two such alarm clocks work for us, then it goes way down to only 1%. What is the probability of being awakened if you have two such alarm clocks? Obviously, assuming we wake up to the alarm, 1 minus that should be the answer, giving us 99%. Again, this is quality control. I hope you realize if we add one more alarm clock, this goes down to 0.001. And that's the idea of quality control. Again, let's look at different method here. So we can use probability of W1 union W2, which has the following formula. I hope you remember when we did probability of A union B. This is probability of W1 plus probability of W2 minus the probability of W1 intersection W2, meaning what is the probability that the first one works? 0.9. What about the second one? Plus 0.9 minus what is the probability that they both work? They are independent, multiply. If you simplify, you end up with 0.99. So this is a second method to calculate this. And here's the third method using binomial distributions. We have n equals to the probability of success is 0.9. Here's the formula. We are going to replace the n with 2, p with 0.9. Therefore, q is 1 minus that, or 0.1. So this is the general formula. We want probability of x larger than or equal to 0, which really means probability of x equals 1 plus probability of x equals 2. That's the meaning of it. Again, it's easier to calculate just one of them, that means probability of 0, and subtract it from 1. So this 2 refer to the fact that probability of 0 and probability of x larger than or equal to 1 are complementary events. So all you have to do, calculate this one, plug in here, x is 0, do the math, and subtract it from 1. And that gives you the same answer. Here's the third method. The only thing I want to add is that the only way it may be the case that the two alarm clocks become dependent if somehow they are using the power and the same plug, and we are out of power, the same plug. And in essence, they become dependent.
During an NFL season, there are 256 games played with 1,307 touchdowns scored. Poisson Distribution?
Poisson
Distribution. What was the mean number of touchdowns TD scored in each game during the season? Round the answer to the nearest 0.0001.
Poisson distribution is the probability of the event occurring x times over an interval. The interval can be time, distance, area, volume, or some similar unit, is given by the formula P of x equals mu to the power of x e to the power of minus mu over x factorial, where e is 2.71828, and it continues indefinitely. In other words, e is the base of natural log. It's just like pi, which is an irrational number, and it's used often. The same thing for e. It's an irrational number, the base for natural log. Mu is the mean number of occurrences of the event in the intervals, and the parameters for Poisson distribution are mu and sigma, where sigma equals square root of mu. So Poisson distribution. So the probability of the event occurring x times over an interval, this is the same concept. Therefore, it makes it a Poisson distribution. In order to find the first part, what was the mean number of touchdowns, we simply divide the total number of touchdowns, or TD, by the total number of games. So mu is number of TDs over the number of games. When we do the math, we end up with this number, and we stop at some point, however many decimals that we need. So that would be part A. Now, into this formula, mu to the power of x, e to the power of minus mu, x factor, I like to replace the mu, but I like to keep e. Sometimes they change it to 2.71828. The reason I keep it as e, because e actually has a lot more decimals, and it gives you a more precise answer.
On January 10th, 2010, the Green Bay Packers and Arizona Cardinals played a playoff game in which there were 13 touchdowns scored. What is the probability that a random game would have that many or more touchdowns?
So we are interested in the probability of x larger than or equal to 13. Now, what this means is that probability of x equals 13 plus probability of x equals 14, and sky is the limit. So 1 minus the probability of x less than or equal to 12 is the proper way of calculating this. Therefore, you have to plug in into this formula 12, 11, 10, 9, all the way to 0. Add them up, subtract from 1. Again, it takes a little bit of a time. As long as we do all this work and show, now all we have to do at this point, just use a calculator. It is just as good. And here's what we do. For Poisson distribution, again, second variables, Poisson PDF, enter mu, and they call it lambda, by the way, as far as the mu is concerned sometimes. X, enter or paste, and if you're using Poisson distribution, it gives you the sum, and it gives you the sum from 0 on. So with that being the case, so Poisson distribution, see there it's asking for lambda, because in many texts they use lambda instead of mu. But if you come across that, remember this is lambda, a Greek letter that is being used for mu in Poisson distribution only. The x value is 12, and you end up with the following answer. Now remember, what is the answer here? 1 minus this. So 1 minus this. You got to subtract this from 1. That's all. So the way I did it, I multiplied it. I subtract the 1 from it, and I got a negative value. Remember, the probability can never negative. You don't have to do that. You know it's the opposite of that, or you multiply it by negative, and there you have it. Again, you can try this with your calculator. If you have any doubts, you want to see how that works. We are going to follow this second variables using the second key, which is in blue here, variables, and I bring it down to find Poisson PDF, and the next one, Poisson CDF. So I'm going to input the information because I want to get this number. So I'm going to put 5.105469. The X value is 12. And as you can see, this is the same number that we got here. And of course, you subtract it from that.
The first column lists the number of touchdowns in a game. This is filled in already. The second column is for the predicted probability that a game chosen at random will have that many touchdowns scored. Calculate these values, round these values to the closest 0.0001. The third column is for your best prediction about the number of games during the season that had that many touchdowns scored. Round these values to the closest whole number.
Perfect. So basically what it means over here, that Poisson distribution, plug in 0, put it here. Plug in 1, put it here. Plug in 2, put it here. So this maybe I should call it the second column because this represents the number of touchdowns, number of TDs or touchdowns. So the second column that represents the probabilities, into this formula goes 0, 1, 2, 3, all the way to the end. And you put them here. Of course, we're not going to do all of them, but just to give you an idea. Now we discuss the next one in a moment. So in this case, if you replace it with 0, I hope you realize that 0 factorial is 0. This number to the power of 0 is 0. All you have to do, calculate this. And that would be the number that goes in here. You are going to multiply that by 256 to put it as the last column. So for that one, if you use this one, it should give you the same answer. I'm showing you this is simple enough. You can see it all the way to here by hand and use a calculator. Or if you use the Poisson distribution in the format that I told you, it obviously gives you the same answer. And now look at this answer. This is identical to this one. Now the result is the probability. We're talking about this column. And how many games? Well, you have to multiply it by 256. Now, because we have to go with the whole number, this becomes 2. So here's this number with many decimals. I put more than 4. You have to really follow what they ask you. And over here, the answer is 1.5522, but we have to round it up. I do 2 more, number 1 and number 2, which means I'm going to use this for number 1 and number 2, and I'm going to multiply both of them by the same number, namely 256 for the next column. So what happens is that if we plug in the next number and we multiply it by 256, we get the probability here. That means if we plug in 1, we get the probability here and the number of touchdowns. And the next one, this is the probability for number 2 with the number of games as follows. So we put those numbers, this one here, this one, both of them are probabilities. It says continue, obviously. And this number goes here, 7.9. Obviously, we change it to 8. 20.23 goes here. We're going to change it to 20. As I mentioned, you just continue and finish up the table.